Hi, my name is Jackson Rankin, and I'd like to demonstrate to you what I've learned about in C++. Um, and you can see that there are a bunch of files here, but I'm only going to go through the Grav Sim. Um, I go through just a regular hello world, um, and then I go through all the different data types in C++, learn about those, then I go to input, output from the console. Then control flow, so if statements, switch cases, stuff like that. Go through functions, go through pointers, which I found super fascinating. Um, Arrays, vectors in memory, classes. So I really love object-oriented programming, so this was super fun too. Structs, which I found a little bit confusing because they just seemed like classes without as much overhead. Then I go through OOP, which I just sort of demonstrate the four pillars, and then file, input, output. So it knows how to take a file and it knows how to output a file. But the thing I want to demonstrate to you is my Grav Sim. So you have your um, um, so gravity is a force. It's the force of gravity is equal to the gravitational constant multiplied by the mass of the first object and the mass of the second object all over r squared. And then it's pointing um, in the radial unit vector direction, which um, it doesn't matter. It's just pointing in the same direction um, um, as where the object is. So it would be pointing in that direction. If you have two objects in orbit, that means that it's pointing towards those objects. Um, and so, but the problem is like you've heard of like the three body problem. We cannot find a solution, a closed solution for a closed form solution for a stable orbit of objects of three similarly sized objects. Like if we had the sun and the moon and Earth, that's a stable orbit. Moon goes around like that as the Earth goes around, and then that's a stable orbit. But for objects of three similar sizes, then there's no sort of stable orbit because, I mean, in the case of the sun and the moon and the Earth does tug on the sun, and the moon does tug on the Earth, but not very significantly. Um, if we had a objects that attracted each other significantly because they're all of similar sizes, then we would devolve into, there would be collisions, or objects would be flung out into space, never to be seen again. Um, so there's no solution to that system of differential equations that will, um, I don't know, it won't tell us the position of those objects over time. Um, Except if you do it numerically, if you assume that for a tiny um, moment of time that the velocity of that object is still, then you can um, sort of track. You can go like, okay, the velocity of this object is constant for that amount of time, like a hundredth of a second in my case. Like this can be a thousandth of a second or whatever. But if we do that, we can sort of track what the object what might do over time. Um, and again, it's not that's Euler's method, I should say. Runge-Kutta order 4, which is what I use here, is sort of accounts for the error in Euler's method. Um, But the problem is that if you have, say, 50 objects, then I have to take one object, calculate the gravity on all those 50 objects, and then assume what the velocity is from that in that moment of time. Then do that again, and then I have to do that for the other 49 objects. So that is an O of n um, efficiency, which is not great. So for a low amount of objects, like 50, or I think I've even done 2000 one time. 2000 took a while. Um, but this will calculate the gravity. Then it will go through each object, um, and it will calculate the gravity on every single other object. And then, as you can see here, it will output all of that to a file. Um, and here's what the file looks like. You have your time, you have the first object, second, your first object's X, Y, and Z coordinates, and then you have that over time. And as you can see, they sort of don't really change all that much. Um, but some bodies, like, yeah, that one gets to 50 60,000 meters away. So, which is quite far. But most of them are, as you can see, are, you know, 6,000, 7,000, 1,000 meters away from the center. So then I have this animation in a programming language called Julia, which I think is fascinating. Julia looks a lot like Python, as you can see, but it uses a just-in-time compiler. Um, so it's able to, it's, I've heard it's almost as fast as C++. Um, so anyway, this program will go through every single row and output, and it will plot the positions, and then it'll go through the next one, plot those positions, which are a little different, plot those positions, and then it'll go through however many rows there are, and it will compile it into an animation. And so you can see that animation here. This is just with 50 objects, but you can see objects are moving around, and you can see that these objects are slowly moving towards the gravitational center. Um, and if you have enough objects, like millions, you can simulate globular clusters. Sorry, like hundreds of thousands. If you have hundreds of thousands of objects, you can simulate globular clusters. And if you have millions or billions of, I think some galaxies are even in the trillions of stars, you can simulate galaxies. Um, so this has a very real application in real life, um, which I found interesting. Like a lot of NASA probes are just calculating, the velocities of stars. So if you have the velocities and the positions of stars over time, for a little bit, you can take that data, put it into a program similar to this, and then see how that object changes over time, like maybe 10,000 years in the future. Um, and so, anyway, that's my program. I hope you enjoyed me yap about this for a couple minutes. Um, but thank you very much for watching.